Hey everyone, let's have a chat about fossilization, right? This is the chapter 13, and we've been starting to understand evolution. We've talked about how we compare and contrast to Hardy-Weinberg equilibrium to make sure things are which type of evolution we're talking about based on the deviation, right? But how do we know? How do we have proofs of that process of evolution, right? One of the proofs that we have is the fossilization of organic remains. And that process takes different shapes. It's not always the same time. So this is what you need to remember. When we talk about compression here, the process of compression was some organic matter falls at the bottom of a body of water, river, lake, usually lake because you have to be still water. Then the fine sediment cover beneath, that's a natural phenomenon that we call atterrissement or earthism, which just means every body of water, of still water like a lake, an ocean, a sea, fills up progressively with sediment coming from the inlets, so river and streams going inside that body of water. And it happens everywhere all at once. So every lake that you know, every sea, every ocean will be filled at some point. It just takes a lot of time for some of them, but some oceans ended up being the floor of the continents nowadays. So things have changed through time, right? So we're talking millions of years. And once you have, it needs at least 10,000 years for a fossil to form, at least. So when the fossilization is underway with sedimentation covering the leaf, now you have compression with the weight of the water or more sediments on top, and that leaves an impression. And more importantly, the organic matter is still present, as you can see here. There's still organic matter in there, right? The next one that we want to talk about is petrification. The petrification process is different in the sense that it's not in a body of water usually, and the mineral that compose the bones, the remains of the animal, are then replaced little by little as water seeps through the sediments and so dissolve the minerals and the bone and replace it with minerals. So when you look at the fossil, you're actually not looking at bone, organic matter. It's been turned into stone, right? The other one is the impression. So in that case, we're not looking at the animal directly, but at the negative of the body of the animal. So an animal dies, usually in mud, and you get a mold, and then in that mold, there is hardening of the mud that happens through time, and we are finding scale shapes. That's how we know feathers were a thing for dinosaurs. It's how we find those soft tissue fossilization process. Without that, we wouldn't know that scale versus skin or feathers versus skin or scale because that is not a bone or a structure, so it doesn't get mineralized by petrification, and it really, really rarely gets through compression. Okay, then we have the cast. So this is something that's interesting because in that case here, you may actually not be looking at the animal directly. You may be looking at a first impression, then a cast, and it's a mold, and then you cast the mold, right, with mud, and that's the mud that hardens, and we find it. So when you look at fossils that are not bones and that are falling in water, we usually find a cast of the animal, and not really the animal itself or even a petrification. So it's different for petrification. It's not a replacement by mineralization. It is a mold cast, and then that's the thing that's hardening. But you can see you don't really find soft tissue in there, although you could technically, but usually soft tissues decay faster, so the sediments around don't tend to form a cast. They just tend to be filled in, right? And finally, you have insect preservation in amber. We can have over-preservation in amber, just not necessarily only insects, right? But it's oozing of a sap that traps insects, and then in there you find DNA, right? So we can look at this in Jurassic Park and understand that, yep, that's how it goes. Jurassic Park, right? They found the DNA and then they just clone it. Not real. We don't do that. For many reasons that you will learn later in this semester. So now that we have all those ways to do fossilization, we need to understand how we compare and contrast with different fossils with each other. So we've looked at the layers, and we already know that if you're on top, you're newer than if you're at the bottom. So we can do relative dating. Whichever fossils you're finding, depending on relative position to other fossils, you can tell which one is younger, which one is older. That is one aspect of datation. It's called relative datation. But we also have absolute datation, and absolute datation relies on the. I wonder if I can move the whole thing. Probably not. Never mind. I can do that. Absolute datation relies on the carbon-14 to carbon-12 ratio. I send you back to your BIO111 lessons, but the carbon-14 is an isotope of carbon-12. Carbon-12 is a stable isotope. Carbon-14 has 2 more neutrons for 6 protons, so it's a 14 instead of 12 in terms of number, atomic number. No, not atomic number, is still 6, but in terms of weight, it's 14. Now, the isotope degrades through time. It's not a stable one, so it means it reverts, and also it's formed through time via cosmic rays of the sun. So at any given moment, a living organism will simply incorporate carbon from its ingestion of matter at the ratio that is available in the atmosphere and on the planet at any given time. And so it would replace the carbon-14 leaving at the same rate as it's incorporating it. Good. But once the animal dies, after death, there is not that process of replacement anymore. So we are finding our way with. We are finding ourselves in a situation when carbon-14 only decays as nitrogen-14, right? So this decay is known, the rate of it, because we know at which rate the carbon-14 decays. And so once the animal dies, we know we can go back in time by simply looking at the rate and the amount of carbon-14 left in the bone at that stage. So if we just calculate that it has that much carbon-14 left, we know it's been 3 half-life, and half-life since the animal died. The half-life is the time it takes for half of the carbon-14 to decay. So you notice that half of the 100% gets you to 50, then to 25%, then to 12.5%, right? Then to 6.25%. And at some point you reach a level at which there is not enough carbon-14 for us to detect, so other isotopes have to be used for older datation, because carbon-14 decays relatively fast. The half-life is 5,730 years, right? So you need to kind of wrestle with your mind to find out how long ago it was an animal, their death, based on the ratio of carbon-14 to carbon-12 that we found, and especially how many half-lives have passed. So you need to be able to work backwards and forward. It's not as intuitive, because if we're talking about 3 half-lives, for example, there should be half, and half, so an eighth of a carbon-14. Eighth of a carbon-14 that was originally, not third or sixth. It's like an eighth. It's a half time the number of a half-life. Now, we know how much carbon-14 was present, the ratio at each time, because we were able to find trapped in the ice cores. So we drill in ice at the poles, and we find air bubble trapped in there, and we can calculate in those air bubble the ratios. And since the air bubbles have different height in the ice, we know exactly when they were trapped. So we know the carbon-14 to carbon-12 ratio through time back as long as we can detect carbon-14, right? So with that, that's the fossilization process, and we'll see each other in the other video, the next one. Bye.